on the force. All right, so let me just remind you what we have seen last week. We are dealing with dynamical system. It's a triple with a semigroup, a set, and a function defined on both. You can think about this as a time, this as a space. And in all the applications, we are going to consider either N or Z if we consider discrete time dynamical system, or R plus or R if we want to consider continuous time dynamical system. And most of the time, this set is going to be a subset of Rn. So if you have these in mind, it's enough. We define what is an orbit, what is a periodic orbit, what is a fixed point for a dynamical system. You should have in mind some pictures. And if you don't have a periodic orbit or fixed point, it gives you a non-closed orbit. Closed orbits are given by either fixed point or periodic orbit. We define what is an invariant subset or plus minus invariant subset of M. It's a set, it's a subset of M such that whenever you take one point and look at the evolution, the evolution is taking place inside the set. So an invariant set contains the evolution of all its points, either for plus direction of time going to plus infinity or minus infinity or both. We also define the notion of limit set, which is in a sense the boundary of an orbit at infinity. We will see it some examples. And it turns out that the limit set is a closed and invariant subset, a limit set of an orbit. The main example, whenever I draw something like this, the main example is the flow of an autonomous first-order differential equation. So you have a first-order differential system, and it is of this form. So x dot of t is f of x of t. We have seen that under very mild condition on f, there exists a solution at least for a small interval of time. And when I represent this, what does it mean? It means I take an initial condition. This is the initial condition. And I solve this equation along for some time. Either I can go up to infinity in time or only on a small interval. So this is the main picture. In this framework of first order differential system, a fixed point is nothing but a point for which we have this x dot of t 0. And we can also study fixed points or what happens around a fixed point. We have introduced three notions of stability. The weakest one was the Lyapunov stability. A slightly stronger requirement was this asymptotic stability. And the most precise one where you have a convergence to the fixed point is the exponential stability. Now, locally, you can also study the stability by linearizing the system. So it means you study, in fact, the Jacobian matrix. And depending on the eigenvalues of this Jacobian matrix and the real part of these eigenvalues, you can say what happens. There is this very important concept, which is, as I said, deeper. And it's used in many fields, even though it has not always this name. A Lyapunov function is a kind of observable, so something you observe or sometimes you can even measure in physics, which has a certain property. In this case, it's decay along the evolution. Sometimes it's increasing, but increasing or decreasing, it's the same. It's just you want to have a monotone behavior, either decay or increase. But Lyapunov is a decay. And whenever you have such a Lyapunov function, it provides some information about fixed points, the stability of fixed points. It provides information about the limit set and also about the constant on orbit. So I gave some explanation about this. So these are important functions. And we will see one or two examples. And then we started finally a short chapter on system in 2D, and we will finish it today. And the first example was Newton equation in 1D, but Newton equation is second order. So you transform it into a first order equation in 2D. And we have just seen that the energy is a constant along the evolution. Okay. So we continue with different examples right now. If you have any question, you can interrupt me. And There are several exercises which I have written. I will not mention them today, but there are several subjects you can work on related to these subjects. And always try to keep in mind some pictures. This is the most important thing. If you have in mind some pictures, then you can reconstruct part of the theory. So the second example in 2 dimensions is it's a famous example, Lotka-Volterra equation. This is related to biology. It's a system with predator and prey, and it is in R2 because we are in 2 dimensions. We consider the following system. I'm not going to explain the biological meaning, but everywhere in the literature you can find why it's a prey-predator system. 1 minus x of t, y of t, and sorry, the y, and this is x of t. And here we have the opposite y of t. And alpha is a real number bigger than 0. So this is a differential system we consider. It's not easy to get, I mean, we cannot get an explicit solution, but nevertheless, it can be studied. I'm going to do something very rough. If somebody wants to write the details, I would appreciate. So how to study this? So the first observation is that we have 2 fixed points. So first fixed point is 0, 0. If you put 0, 0, the derivative, you get 0 on the right-hand side. And so it's a fixed point because the derivatives are 0. With my convention, I should put a transpose here. And the 1, 1 is also a fixed point because if x and y are both 1, again, you get 0. So you have 2 fixed points. But there are other solutions which are easy to get. If we look for a solution of the form, solution for initial conditions. So with two types of initial conditions, we can find a solution. The first initial condition is 0, y 0. If you put 0 for x, then you get that the solution, I'm going to write like this for the solution. This is a notation, so it's the evolution for this initial condition. And you find that this is 0, y 0. And there is a second one you can easily find. There is unfortunately a small problem of notation. This T is for transpose. So let me do it in yellow. This T is for transpose. It has nothing to do with the time. In the notes now, I'm using a specific font for this. And the solution with this initial condition is x0, et, and 0. Both x0 and y0 are arbitrary real number. So if you do a representation of what happens, so this is R2, we have 2 fixed points, 0, 0, and 1, 1. And the solutions which are mentioned here correspond to these axes. So if you pick x0 here, and you look at all possible time, it covers this line. If you do the same for the x0 negative, it covers this line. This is a second solution. And the other one would be here. So we have some solutions which are explicit, but it means, remember, orbits cannot cross. So it means all other solutions, if we start with an initial condition here, I can only stay in this part because I cannot cross. It would be the crossing of two orbits. It's not possible. So it means these four regions can be studied separately, and usually we consider this one. This is the one because it has a fixed point. I don't know exactly what happens here, but this one is the one which is interesting because it has a fixed point. Probably with a biological interpretation, this is true. If these X and Y represent populations, it's better that they are not negative. Okay, so we shall concentrate on this. As I said, it's not possible, as far as I know, I didn't check carefully, but it's not possible to have a very completely explicit solution, but there is a trick. And this is where I play a little bit like the implicit differentiation. Suppose that we have something, I don't know what, I do this picture, but for now I don't know. But I suppose that locally the solution can be written as a function of x, so y. Suppose y is locally the function of x. It means this, I can parameterize this part of an orbit as a function of x. And then what people write, and as I said, it can be better written. So if a student wants to write it properly, I would be happy. We look at the derivative of y with respect to x. And this is, I close my eyes because I don't want to see this. This is a trick that we often use. And then you're going to write this is dy over dt, and then dx. Of course, everything can be written in a better way. Inverse. And if you do this, then you end up, because we have derivative of y with respect to t, it's written derivative of x with respect to t, you end up with this system, oh no, with this equation. This is x minus 1y divided by 1 minus x. And we can do a separation of variables. Probably for a second year, it's a good exercise to write what we are exactly doing here properly. What it means with implicit differentiation, inverse of a function, and so on. So if you do it properly and you do the separation of variable, you find that the solution, you end up with the following equation. The solution is this. So we have an equation f of y plus alpha f of x is equal to constant with f, a certain function precisely that you obtain by the separation of variable. F of x is x minus 1 minus. You have to work a little bit, but it can be done. And so what you end up, if now you study this, you can draw the orbits. And the orbits are indeed of this form. There is a better picture in the notes. So it means if you look at the orbit, they are all closed and they contain the point 0, the point 1, the stable point 1. So it means how you should understand it is if you pick up initial condition here, the evolution of this will be a closed orbit like this, so a periodic solution. And this can be obtained by just doing this precisely and then studying this. It's an exercise to do it properly. I'm just sketching. But it means for this system, in this region, we have only periodic orbits. They cannot cross, remember, and a fixed point. So it's a rather simple system. But it's a, okay. And it has some interpretation in biology. And there are some more complicated systems. If you make it a bit more complicated, you have additional properties, and it's probably more interesting, but it's also a bit more complicated. This is the first example I wanted to mention today. If you have any question, again, you interrupt me. And there is a second one which we can also study, and then we will turn to a more general theory. So this is called the NR equation. It's also in R2 because we are in.
Question for the solution part. Can't we just eliminate the one because the right-hand side is a constant, so you could just say.
I think so. I think so. I was also surprised. I didn't do, I didn't check all the details, but I suspect that, yeah, this one is not so important. It's probably, yeah. Okay, so then now you have a next report. I'm not saying that this is the only way to do it, because indeed, if you eliminate this one, it's still a question. It's probably a kind of normalization.
And the one plus
no, but if you can play with this constant, the one, they will just count. But it's probably a normalization we want to have. Or it's a way to index these orbits. So the indexation will probably depend on if you keep the one or not. I didn't do the detail, sorry. So for this, I consider first a function f from R to R with f of 0 equal to 0. It's a one variable function. And so then the system we consider is the following one. So it's in two dimensions, as I said, it is x dot of t, y dot. By the way, there are two ways to write such system, and both are fine. Here I keep the idea, on the blackboard, I keep the idea that it's a vector, so it's a first order differential system. So I have a vector, but if you write with some curly bracket, of course, it's equivalent. Yeah. Except that you would have two equalities instead of one. Okay, so this is the system we consider, and the f is a function of one variable, so this is correct. Fixed point is 0, 0 again. You can check that 0 is a fixed point. You use this condition on f, 0 is the fixed point. And now we are going to do the analysis around this fixed point, and we will learn something. So the first, if f of x is bigger than 0, oh, I have probably a contradiction in my notes, so I will correct it. It cannot be bigger than 0 on an interval around 0 because it's 0 at 0. So there is a small contradiction. So I have to write on minus epsilon 0 union 0 epsilon. Otherwise, yeah, if it cannot be strictly bigger than 0 if f of 0 is 0. So there might be a mistake. I will check. But now it's meaningful. So then if I'm going to consider, I told you observables are important. So I'm going to consider a Lyapunov function or one observable given by the following thing. So we consider the function, and it's a natural notation. Instead of L, I will call it R because it's related to the radius. We will see. I consider this function of two variables like this. I call it R. And the point is the following. If x of t, y of t transpose, if they satisfy the differential equation, so this, so if we have solution of this, let's compute d over dt of r of x of t, y of t. Let's compute this. It's a derivative of a composition, but this is rather easy. That when you differentiate, the 2 will cancel with the 1/2. So you obtain x of t, x internal derivative, x dot. I put a big dot, but this is just a small one, but otherwise it will not be visible. Plus y of t, y dot of t. So this is what you obtain. Now you know that these are solution of this equation, so you can replace. And I let you do one more line. You obtain minus x of t, f of x of t. There is one more step that I didn't present. You use the fact that it's a solution. And by my assumption, this is smaller than 0 if x of t belong to, again, there is probably a mistake in the notes. It belongs to this union of two intervals. Yeah, yes, there is a minus sign. Just check. I haven't done. And the Lyapunov function, we choose that they are negative. They decay. So it means this is like a Lyapunov function because the Lyapunov function decay along the evolution. Here's a derivative decay. So it means R is a Lyapunov function. On this, and you observe that there is no condition on y. So in fact, it's a Lyapunov function on a kind of tube or rectangle or two rectangles because you have this and the same, no constraint on y. So it's a Lyapunov function. I don't. And by the theorem that we have seen last week, only I don't remember the number, but of last week, about Lyapunov function, you get that 0, 0 is, and it's strict. There was two conditions last week in the theorem. One was weaker if we have a non-strict, but this one is strict. So it is asymptotically stable. So it means close to 0, they would converge to 0. The solutions would converge to 0. And it's probably true on a domain like this because, as I said, there is no constraint on y. Right. So this is in the first case when it's positive. Now, you can guess in the other case, if this is negative, so this is the second case. If f of x is negative on the same interval minus epsilon 0 union 0 epsilon, you can do the same computation, and what you obtain is that d over dt of this function r of x of t, y of t is now strictly positive. I haven't developed any theory, but still you can guess what happens in this case. As I said, this is an observable which represents the distance to the origin. So if you think about it, it means along the evolution, this distance is increasing. So it means we are going away from zero. So it means, I don't know how, but we escape from zero. And I should probably also do one here. So depending on the sign of this expression, we have this behavior, either attracting or repulsing. All right. I will correct the notes about this small mistake. But in fact, we can say more. And this is, if you impose more on F, you get a nice picture. So I'll just write, if we impose more on F, we get the following theorem we get. So it's a very precise asymptotic behavior for this system. So I'm going to suppose that first F is once continuously differentiable. This is not so strong. I will assume also that F is odd. You all know what is an odd function. I will do a picture. So it has a certain behavior. And in particular, this implies that f of 0 is 0. All odd functions have to vanish at 0. So the condition I had imposed on f is satisfied. I also impose that f of x is 0 on an interval, strictly smaller than 0 on an interval 0 alpha, and f of alpha is equal to 0. And the third condition is that f of x, or f more precisely, is increasing on alpha infinity, and its limit, it really goes to infinity. You don't need all these things, but it's simpler. So what is a representation of this function? Be careful, this is not a representation in R2. This is just a representation of f. So f has to be like this. And since it's odd, it has to be like this. This is alpha minus alpha. This is the f I have in mind. And look, it's still, so we are probably still on this case if f is negative, or no, more precisely, if f has this shape near 0, we are in this framework. So it means 0 is going to be repulsive, but we can say more. So if f satisfies this, then there exists a unique periodic orbit which encloses 0, 0. So enclosing 0, 0, and every other orbit converge to it. Except, of course, except the stable fixed point 0, 0. So if we do a picture, and there is a picture in the notes, we are in it's the first rather non-trivial system. Now this is a picture in 2 dimensions, so we have x and y. 0 is a stable point. we have one fixed orbit, which is like this. This is a fixed periodic orbit, a unique one. And all the other one will, if you start with another initial condition, you will just converge to this. And the same from outside. If you start with the initial condition, you will just converge to it. That's what happens for this system. And the only point which is, so this is a periodic one, there is only one. All the other orbits will either converge from inside or from outside. So it's a rather famous result. The proof is not completely trivial. It's a bit long, but if somebody is interested. And remember, orbits cannot cross. So it means if you take another initial condition inside, it will converge also to the boundary, but it cannot cross the yellow one. So it means it will have to be like this. So you have a very strict rule about non-crossing. Any question about this? Any comment? So as I said, some of these assumptions on F can be weakened a little bit, but it's not my aim. And probably there is I wouldn't be surprised that there is you can play with F. If it's not strictly increasing, you can probably prepare a second closed orbit, but then some trajectories would go to the first one or to the other one. So you can probably play a little bit with this. And again, I put some exercises related to this Liénard's model. But as you can see, 2-dimension is very special, and we are going to explain it. For example, if you look at the cover of these notes, this is the cover. This cannot happen in 2-dimension. If you want to have such a complicated picture, you need to go to higher dimension. So one of the next statements is precisely a proof that this cannot take place in 2-dimension. And for studying this problem in higher dimension, we will need to develop new tools. So this is 5.4. These are limit sets. In 2D. So remember what is, oh, by the way, what is the limit set for all these trajectories? The limit set for all these trajectories is the blue periodic orbit, because you are converging, or any initial condition is converging to the blue one. So you can find a sequence of time which converge to any point around this one. So you can see the yellow one will converge to the blue one. So regularly it will come closer and closer to any point. So this is what happens. So you can wonder, and this is true, can we in 2-dimension, can we understand all these limit sets? And the answer is yes. In 2D, we have a good description of all limit sets. And it's thanks to a very special property in 2D, thanks to, this is called the Jordan curve theorem. I already mentioned it last week. And in fact, you are all familiar with it. If you draw any closed curve which do not intersect, so this is a closed curve which do not intersect, it defines two regions of R2. You have the interior part, and you have a big exterior, and there is no other things. The Jordan curve theorem tells you any closed non-intersecting curve divides the plane into two regions, one which is bounded by the curve and the other one with point going to infinity. Yes?
Periodic orbit, doesn't that necessarily mean the orbit intersects itself?
No, the orbit is a final orbit. It's one time the blue region. I mean, it's just, what is the definition of the orbit? It's all these blue points. What does it mean that it intersects itself? It doesn't mean anything.
That starts somewhere here and
No, but
there, and they both end on the blue curve.
no. The orbit is a final object. You don't look at the time. Remember, gamma of x is a set of all phi of tx for all t, let's say, in R. I'll take the simplest case. So it's a set of points. You don't care if you go here 3 times or 5 times. And then a set doesn't mean anything that it's self-intersecting. So no, there is no contradiction. But it's a good remark. So what is this Jordan curve theorem? I already made the pictures, but the statement is that every non-intersecting, of course, non-intersecting, I don't want to consider this because then the statement has to be adapted. But every non-intersecting continuous, oh yeah, I didn't mention, but of course it's continuous closed curve in R2. This is only true in R2, divides R2 in 2 regions. And one is big because it encloses everything up to infinity, and the other one is rather small. And of course, if you think about it in R3, this statement is simply meaningless, except if you start with surface, but we are dealing with trajectories, and a trajectory is more like a curve. It's not a surface. And so, as I said, we can describe essentially all limit sets. It's a rather long statement, but it's a nice one. It's called generalized Poincare bending. Okay, so it has a name. So what it is, we are in this framework, so I have to be precise. Let M be a subset of R2. We are in 2 dimensions. Be open. And we assume that F is a C1 function on M with value in R2. Hope it's not mine. No. So we are in this setting, and I consider point X in R2. In fact, in M, otherwise it wouldn't be well defined. I consider a point in M, and I assume that its orbit, gamma. Yeah, there is always a small confusion. When I speak about gamma plus 1, in fact, there are 2 statements. One for T positive, one for T negative. So sometimes I use a sentence with a plural, sometimes it's singular. I'm not sure I'm always consistent, but it's usually 2 separate statements. So we assume that gamma plus or minus is contained in a bounded and closed subset of M, of R2, yeah, of M. So we are in this setting, we have a big set M, which is open, and I assume that if I take a trajectory, it stays inside this box. So this is X, and I assume that gamma plus, this is gamma plus of X, so the evolution of this point stay in a closed and bounded set. I usually represent such a set by a box. Okay. And we know something we have seen in this case. I just recall that it implies that the limit set, I already mentioned this, the limit set is non-empty and connected. I just record this. And I will assume one more thing. I'm not sure about this assumption of M, so on close on M, and assume that omega plus or minus of X, now we know it exists, we know it's contained in this box, contains only a finite number of fixed points. So this assumption is not completely trivial. And for third or fourth year student, you can wonder if what would be a system with a limit set with an infinite number of fixed points. There are probably examples, but they are outside of this theorem. So it would be nice to have a counterexample, so a system with an infinite number of fixed points in the limit set. But you will see why I need this assumption. So then that's the statement, I mean the assumption, then one of the following alternative hold. So, and we have only three. Either this set, this limit point set is a fixed point. It's only one fixed point, which is the simplest case. Probably the picture I have represented here is of this type. Omega plus or minus of X is a periodic orbit. This is typically the example we have seen before with Yenad. It's a periodic orbit. And there is a third one which we haven't seen yet, but I will represent it, is that W plus minus of X consists of finitely many fixed points, finitely many fixed points. And I'm going to call them xj, j from 1 up to a certain n, but it's finite. And some closed, non-closed orbits. Gamma of y between them. So between the points, between them. So the them represent the points. And I gave an explicit example in the notes, but I'm going just to draw the picture. But there is a system of equation which lead to this. So what is it? We are still in two dimension. So we have, and the system is like this. You have two fixed points. So it's one example. I'm not saying that, but I want to explain. And So as I said, fixed point we have already seen. This we have already seen. This is a new situation where you have a finite number of fixed points. In this case, we would have two curves which link them. So what does it mean? It means if you start with the initial point here and let the time evolve, you would move along this curve. Or if you start here, you would move along this curve. These are open curves, so it means you never reach this fixed point. This is clear because, again, two orbits cannot intersect, so you would never reach exactly this point, but you can approach it. And this is an example of this W plus minus. So it means in this example, any initial condition would do something like this. And it would approach this yellow region, but never touch it, but approach it so that the limit set would be this yellow region. Of course, if you're on one yellow part, this is different, but here the statement is that for given initial condition, the limit point is made of two fixed points and two curves linking them. And another example where I also represent it in the notes, and there is an exercise related to this. It's also in R2. You have one fixed point at 0. Now it's interesting because in the statement linking this point, it means one closed curve can link a fixed point to itself. So we have this double things. So it means we have two open orbits like this. They never touch the fixed point. And what happens? If you start with any point inside, you would approach this yellow curve. The same here, you would approach this yellow curve. And probably outside the same. I don't know exactly what happens outside. Or outside, you may go to, no, you may not go to infinity. You would probably approach the curve. So this is all what can happen in R2. Either one fixed point, a periodic orbit, we have seen examples, or this dual situation where you have some fixed points and some curves linking them. And then all other points would just converge to them. Yes?
What is the periodic orbit containing a finite number of points? Because doesn't it have like an infinite number in R?
No, but look, it's for given x. So we can have this picture and maybe we can have it a second time here. There is no contradiction. I'm not claiming that, of course, simple system would probably consist only on one picture like this, but it says that given x, we can have only this. It's the asymptotic set or the limit set for given x. It's not that all x would lead to this. So be careful. So I can probably construct a system where I have the same picture here, and there would be no contradiction, except that a given x here would either go to infinity or converge to, because going to infinity is also possible. There is the limit point set is empty. So there is no contradiction. Is it better now? No, it's not a trivial theory. And as I said, I'm wondering if we can find a so, you know, if we have an infinite number of fixed points, probably this picture breaks down because we would not know how to link them. So I'm wondering if there is an example, and probably you can find one on internet, about such a system, but with an infinite number of fixed points, what happens? I don't know. But if somebody finds something, it would be a nice report. Any question or remark? But you see, this theorem is very strict. In 2D, there is nothing else. So you don't have any more fancy pictures as this one on the cover. So this you need to go to 3 dimension because of Jordan curve theorem. So in order to move to higher dimensions, we have to develop new tools. Because, yeah, we will see. Okay, so the next chapter, which is number 6, is dynamical system. In a higher dimension, or in any dimension, but essentially it's in any dimension. So I don't want to restrict the dimension. And as in this last part, we shall essentially consider, I think it's uniquely, or consider, we shall consider continuous time dynamical system. So it means that time is going to be on R plus or on R. So we shall consider continuous time dynamical system. And we shall assume one more thing. In Rn, and by the way, remember one thing. It's not so important, but when I'm speaking about closure, the closure of a set, in an arbitrary set, it doesn't mean anything. You need a good case is Rn because we know what is the closure. More generally, you need a topological space. But if you do some dynamical system in arbitrary setting, and sometimes it's interesting, the notion of closure, you have to be careful what it means. So we consider the continuous time dynamical system in Rn, and we shall assume that they are globally defined. So what does it mean? I introduced it, but let me recall it. It means I can define it for all time. T can go to plus or minus infinity. If we have some trajectories which explode before reaching infinity, then it's difficult to speak about these limit sets because the limit sets are precisely defined as points when t goes to infinity. Okay. So we assume that they are globally defined. If they are not globally defined, then you need to change a bit the approach. Okay. So the first section, which is not trivial, is about attracting sets. So I want to recall something I have already mentioned, but no, it's no more on the blackboard. That for this dynamical system R, M, and phi, and M is in Rn, we are in this framework. So for this, I recall that for X in M, the orbit gamma plus minus of X is a set of phi of Tx such that T is either bigger or smaller than 0. So I put plus or minus T, which means either I consider T going to plus infinity or T going to minus infinity. And these points are in M. So this is the definition of one orbit, or one forward orbit or backward orbit. But now I want to consider not only one point, this is one initial condition, but in order to have a richer theory, I want to consider a set here. So instead of, let me just draw a picture what I want to consider. Let's say this is M. Instead of just looking at one trajectory, I want to consider family. So I want to consider, because something can happen when you consider family. For example, it becomes larger and larger or whatever. So I want to define the evolution not of only on one point, but an initial set which I'm going to call lambda. So that's the new object. Or X, sorry, I will consider first capital X. Yeah, I replace small x by capital X in the next definition. So it means I consider an initial set capital X in M. So we consider more generally, I consider capital X inside M, a subset of M. And then it's natural to define gamma plus minus of capital X, just the same. The set of phi of Tx inside M, so that X is in capital X and plus or minus T are bigger or equal to 0. And of course, you can immediately observe this is nothing but the union. So it's a bit trivial, the union over all X in X of gamma plus minus of X. But this level, I haven't gained so much. What will be important is when we look at the limit set. The limit set will be richer. So this is a picture. I start with a X, and now instead of just one trajectory, I look at a family of trajectories. Okay? And we have seen this set gamma plus minus of X is plus or minus invariant. Remember, this is a trivial observation. If you take one trajectory, okay, and you pick any point inside, then it will also be inside. So this is a definition of invariant. So invariant set is any point inside has its trajectory inside. By definition of one orbit, it's true. So this is easy observation. But we also have gamma plus minus of X closure. This is a less easy, is plus minus invariant. Be careful with this picture, is a bit misleading. What is if I do this, what is a closure? You are going to tell me the set itself. But for example, let me draw a trajectory, which is a bit more complicated. If I do this one, where I come closer and closer to a certain point, okay, I don't know how to represent it, but then the closure will also contain one point which is maybe not on, for example, it can be a fixed point. So the closure can be a bit larger than, usually it's a bit larger than the set itself because it contains a boundary of this set. So you have to check that when you take into account the boundary, it's also invariant. And for the example I mentioned before, Oh, yeah, let's come back just to this example I did before. So if you start here, okay, and you let it evolve, the boundary, the trajectory, the orbit will just be this blue part. But when you take the closure will be the blue part together with this, right? So you can see the difference. The gamma of x was just this infinite spiral, while when I take the closure, I also have the boundary, right? Sorry? Yeah. Yeah. Probably, yes, probably the closure is made of the disjoint union of the set and its limit set. Yes. Okay. So now this was for one trajectory. You can think the same similarly. If now you take this tube, you have gamma of capital X plus or minus is plus or minus invariant. It contains all its points in the same gamma plus minus of capital X closure. It's less easy to represent, but if you think about the closure, you can get it is plus or minus invariant. None of these statements is completely trivial. You need to play a little bit and imagine a little bit. Okay. But now, as I said, I want to understand the limit points of the limit set of these. And we will see the difference. And we will work on a concrete example to really see the difference. It's visible in the definition, but on a concrete example, we can see it more clearly. For the limit set, I want to define W plus minus of capital X. So far, I don't have any definition for this. You could say, oh, because of this, I just take the union about the union over X of this, the limit set for each trajectories. But this is not a good notion. So let me give you the definition we need to use. This is a set of y in M such that there exists a sequence Tn and Xn. This is a sequence indexed by n, having to do with Tn going to infinity. Remember last week you asked me this, so I really want to look at large time. So Tn goes to infinity or plus minus infinity, depending if I look at plus or minus, and limit when n goes to infinity of phi of Tn xn is equal to 1. So please pay very careful attention to the fact that I allow both Tn and xn. And now I'm claiming that this set contains the union over all x belonging to capital X, omega plus minus of x. But in general, you don't have an equality in general. Why? Because remember, okay, maybe I should recall what is this guy just to make it clear. You will see that you have more freedom. I just recall W plus minus of X is a set of Y in M, so that there exists a sequence Tn and in N with Tn going to infinity, when n goes to infinity, and phi of Tnx is y. So you see the difference. Here, for given x, you have this freedom over n, pick some time. Here we have much more freedom. We can change the x. And as I said, I will do a concrete example where we can see the difference. I can play and jump from, this is really what we do. We jump from one orbit to another one. By changing xn, I jump from one orbit to another one, while there I'm not allowed. There I'm stuck to one trajectory, on one trajectory. So this is why this definition is more general than just the union, and this is the one we need for this topic. Yeah. Yes, you are right. Xn is probably in, wait a second, you're right. Okay, in my notes, indeed, I guess I need to check, but I guess this one is in X. Yes, I think so. We have a sequence in capital X. So let me make this picture a bit bigger. I will double check, but I think this is correct. So let's suppose I take this capital X at the beginning and I look at its evolution. Okay. So with the first picture, I start with the X and I look at just one trajectory. And along this trajectory, I have T1, let's say T2, T3, and so on, right? This is the first ID. Now I can do something different. I can take X1 here, X2 here. And so it means I also look at this one. And I'm allowed to take this point, X1, T1, X2, T2, X3, T3, and so on. So you have this additional freedom of jumping from one trajectory to another one. And we will see on a concrete example. So you're right, probably, but I will double check that this is what is missing. In my notes, there is also this typo. There is no capital X. It is. Okay, so it's my handwritten note. Okay. Let's work on a concrete example just to see clearly the difference because it's interesting. So it's a baby example in a sense, but we can learn something. And by the way, I would be happy if somebody produce a picture for this situation, you will see. I didn't draw any picture. So I consider this system. Why I'm calling it a baby one, look, the system separates into two independent systems. So you have two independent equations. The second one, you can solve it explicitly. The first one, probably not, but they do not interact. So the first observation is that the point X is equal to plus or minus 1 is a stable. I did not check the stability, but I believe it is stable fixed. So you can do it. It's a stable fixed point, either by linearizing or by a Lyapunov function. Is a stable fixed point for the first equation, or R stable fixed points for the first equation, and 0, then X is equal to 0 is unstable, And for the second one, we have the solution is Y0 times E minus T. is a general solution of the second equation. So if you draw the phase space or the flow of these trajectories, and this is what is not in the notes because I was lazy doing any picture like this. So we are in R2, X, Y. As I said, you have a fixed point here, a fixed point here, and 0. And all trajectories are either like this or they are like this. And you can wonder what happens on the real axis. So 0 is a fixed point, and you have something like this on this axis and something like this on this one. And probably so this is probably the picture of this. So now let's compute. Good to still have this definition. Let's compute B. No, sorry. The limit set. I do it for W plus. It's a bit easier. Oh yeah, when I do this picture, is always when t goes to plus infinity. Otherwise, you have to reverse these arrows. W plus of the ball of radius R on center 0, center 0, 0. And I need to put a transpose if I want to be consistent. And I'm going to take R bigger than 1. So it means I take a ball like this, and I want to look at its limit set. And I will also do, I ask this, no, let's first look at this, and then we are going, so this is the first set, and then we will look at the union for all x in the same ball of gamma, no, of limit set W plus minus, or plus just plus of x. Just to see the difference. Can you guess without looking at the note? What is the first set? And what is the second one? I want to show you the difference between these two things. So again, here I just take all trajectories individually, and I take the union. Here I consider the limit set with the definition there of this all points in this ball. So I'm claiming that for the first one, it is the interval minus 1, 1 times 0. I will do a representation, while for the other one, it's only 3 points. That's what I'm claiming. So let's try to see this. Take one first, the second one is easier to see. Take any point and look at how it evolved. It would either go to minus 1, 0, or to 0, 0, or to 1, 0, right? This is a third, this one with only 3 fixed points. What about this one? Now remember, you have this ability to jump from one trajectory to one trajectory, from one orbit to another one. Of course, if you just follow one, you will end up to this point. But if you are allowed to look, we have plenty of trajectories which are like this, right? And if you are allowed with this definition to jump from, so you go from here to here to here to here, here. I mean, time is increasing, but you end up, you can come as close as you want to any point on this real axis, on this x-axis, by jumping from one orbit to another one. This is the freedom you have in this definition here. And of course, the same on the other side. That's why you get all points between. It's a bit misleading because as a set, it's correct, but in fact, it's made of, yeah, this point doesn't move, but as a set, it's correct. There is no problem. So you can see here, think about it carefully, but we can see clearly the difference between these two concepts. And the first one gives you much more freedom. Because otherwise, wait, yeah. No, wait, what happens if I take a smaller?
Well, it is that you cannot go to one.
No, I said, yeah.
Once, and again, it's the.
You need to jump from a trajectory that's going towards one to a trajectory that's going towards -1.
Okay, for now, I don't see a real difference. That's a good, so now you have a job. Is it a restriction, or why did I take r bigger than 1? Is it correct if we take it smaller? Do we get the same thing? For now, I have the feeling, but we need to think more carefully about it.
Question, how is 0, part of the union of the limit set? Is it a fixed point?
Yeah, it's a fixed point.
But we said that x equals 0 is unstable there.
No.
No.
It means, of course, what means unstable, it means if you move away just a little bit, you will move away forever. But if you are just at 0, 0, you can see 0, 0 is a solution.
Okay.
So no, it is.
And none of the orbits go to.
No, none of them go to 0, 0, but if you are at 0, 0, you stay forever there. That's why I was thinking it's a bit misleading, but no, it's just a set. As a set, it doesn't matter that we take all these points at the same level, but you're right, 0 is in a sense isolated. Then you have the other one that you get by another approach.
Yeah. So there's only one orbit, which is it starts at 0, 0. That's the only orbit.
The only one. Yeah.
Why do they stop at -1 and 1?
Because they are attracting for the.
If you are going to make a series that's converged to like -1/2 0, why can't you make -1 plus -1 minus epsilon?
No, -1 minus epsilon.
No, sorry, -1 minus epsilon 0. The value of x is smaller than -1. But
Here.
-1 and minus air. Yeah.
No, because you would have to start at okay, now I see why. If you don't take if you don't put any, if you take the starting point all out, no, which is not meaningful, but no, you cannot get here because you would have to start at on trajectories which are not inside the ball. If you want to reach this, you would have to go to infinity, probably. So no, this I'm pretty sure this is really the limit. But now why 1/2 is not fine, I'm not completely sure. No, okay, let's move on. HeavyDo is going to solve this problem for next week. So we have seen that this new concept really contains something different. We don't know yet if it is the right concept, but at least this notion of trajectories for family or for set gives something different. I want to recall the notion of distance. So I recall one thing for a set lambda in Rn and any point x in Rn. What is the distance between x and a set? I just need to recall this is the infimum over all y in this set lambda of the Euclidean distance x minus 1. This is quite natural. If you have a set lambda, a point x, you look at all distance, and then you try to find the minimal one, and it gives you the distance between the set lambda and x. And similarly, if you have now two sets for lambda 1 and lambda 2 inside Rn, what is the distance between lambda 1 and lambda 2? You can easily guess now it's an infimum over two things. It's an infimum over x belonging to lambda 1, y belonging to lambda 2 of this Euclidean distance between x and y. Okay. And so I need these two concepts of distance. I'm already forgetting the two things I have to check, so I need to write it. Okay. And what is the last definition, or just before the last? I want to define what is, at the end, I want to define attracting regions. So, okay, let me start with this definition. I start with for an invariant set, or for invariant set lambda in M. I don't know why I moved from x to lambda, but now it's invariant. So I define with set W, it's a capital W plus or minus of lambda. This should remind you the omega, the limit set omega, so the notation is similar, but it's a capital W plus minus of lambda. It is a set of x in M such that the limit when t goes to plus infinity, the distance between phi of tx and lambda is 0. So what does it mean? I fix an invariant set, and I look at all points which are becoming closer and closer to this set lambda as t goes to plus or minus infinity. So on this picture, if I fix, it can be a set, so I can take, for example, just one point. Then I would get the half, probably the half space here, because all these points are becoming closer and closer. On the other hand, if I fix the point 0, I would probably obtain only these two lines. And you can now take another invariant set. Of course, you can take, this is also an invariant set. You can wonder which points converge to it. So this is a definition of this W plus y minus, a set of points which are approaching your invariant set as along the evolution. And it's still in the definition. They have a name. W plus of lambda is called the stable set. I would say of lambda because it depends on lambda, and W minus of lambda is the unstable set. Again, of lambda. Yeah. If you go with t going to minus infinity, it is a set of points which are finally going away. So you have to, for me, it's more difficult to imagine what does it represent with t minus when t goes to minus infinity. It's a bit easier with t goes to plus infinity, but you have to reverse the picture for t going to minus infinity. And there is one or two observations. One or two observation is that, now we'll finish with the name observation, is that these W plus or minus of lambda are invariant sets. They contain all orbits of points inside. They are invariants. And they contain lambda itself, which is a bit, it's a bit annoying from my perspective. Look, of course they contain it, because if you start with a point which is already inside lambda, since this lambda is an invariant set, it stays inside. And by the way, the distance between one point inside lambda is, of course, 0. So it means this invariant set contain, of course, it will play a role, but they contain the set lambda. And they are invariant because they contain the evolution of all their points. And they have an additional name. So let me finish with this. If W plus of lambda is open, then we say that omega is, lambda is attractive. And call this W plus of lambda its domain, or a French word, it's I don't know how to say it in English. Bassin. Who can teach me? I have to write it. And its domain, or it's, because this is a French word, bassin of attraction. Basin. Yeah, one native. Basin. Okay, basin of attraction. Yeah, you're right. Bassin. Okay. Basin of attraction. All right. So this is all for today. So, but please, what you should remember is it's important. One trajectory, just looking at the evolution of one point, is not enough for our current investigation. In order to understand these kind of pictures, just one trajectory is not enough. We need to think about sets and the evolution of sets. And we have already seen that the limit points for the evolution of a set is richer. It contains more than just looking at the evolution individually. And we will continue in this direction next time. And we finish with this definition of what is this domain or this basin of attraction. So please keep in mind these things for next week. We will continue. It's an important topic. All right. If you have any question, you can ask me now or later.